standards, space huge, specialized co-rooms, minimal, standard server racks, maintenance manual / on-site automated / remote upgrades hardware heavy / expensive software based / agile. 6. Convergence of voice, data, and video. Soft switches enabled a single converged architecture, old world, voice on PSTN, data on the internet, TV on separate coax networks. New world, soft switch era, voice, video, and data all unified over IP triple play / quad play services, VoIP plus internet plus TV plus mobile. The magic of the soft switch lies in its move from circuits to packets. In the legacy era, voice, data, and video each lived on their own islands of infrastructure because they had different physical requirements. The soft switch acted as the bridge that allowed them to share the same digital language. Here is how the soft switch enables a single converged architecture. 1. The common language, IP, Internet Protocol. The most fundamental reason for convergence is that a soft switch treats voice and video as just another form of data. Legacy, voice was a continuous stream of electrical signals on a dedicated wire. Soft switch, voice and video are chopped into tiny packets of digital data, wrapped in an IP header, and sent across the same fiber optic cables as your emails and Netflix streams. 2. Separation of payload and signaling. Because a soft switch separates the control logic from the media gateway, it doesn't care what the payload is. The control logic, call agent, handles the invitation to start a session, whether that session is a phone call, a video conference, or a file transfer. The media gateway or SBC, session border controller, handles the heavy lifting of moving the bits. This allows a single signaling protocol, like SIP, Session Initiation Protocol, to manage multiple media types simultaneously. 3. Unified transport, the pipe efficiency. In a non-converged network, carriers had to maintain separate pipes for different services. A soft switch allows for statistical multiplexing. Since voice, data, and video are all packets, they can share the same bandwidth. If no one is talking on the phone, that extra bandwidth is instantly available for someone downloading a large file. This flexibility is impossible in a fixed circuit 5S environment. 4. QoS, quality of service, orchestration. One major hurdle to convergence was that voice and video are fussy. They can't have delays, latency, or they sound robotic. Data, like email, doesn't care about a 1-second delay. Soft switches work with modern routers to implement QoS tags. The soft switch can tell the network, this packet is a voice call, put it at the front of the line. This packet is a YouTube video, it can wait 10 milliseconds. This orchestration allows high-quality voice and video to coexist with heavy data traffic on the same physical wire. 5. Application integration, the triple play. A converged architecture enables triple play, voice, video, and data, through a single user device. Example, because of soft switch convergence, you can receive a voice call on your laptop while watching a video, and the soft switch can see both streams. It can automatically lower the volume of your video when the voice call starts. In a legacy 5S world, the phone and the computer were two different worlds that couldn't talk to each other. Summary of convergence feature: legacy architecture, soft switch, converged architecture, network type siloed, PSTN for voice, IP for data, unified, all IP, switching, circuit switching, physical path, packet switching, virtual path, primary protocol SS7/TDM SIP/IP service delivery, separate wires /billing, one pipe /1 bill. 7. Mobile networks transitioned, 2G rightward arrow, 3G rightward arrow, 4G, mobile cores moved from circuit switched MSCs, 2G/3G, to IMS soft switch based architectures, 4G and 5G. Soft switches were the stepping stone to VoLTE IMS, IP multimedia subsystem, 5G standalone calling in mobile networks. The soft switch was the catalyst that moved cellular architecture from specialized radio boxes to the flexible, cloud-native systems we use today. It essentially flattened the mobile core. Before soft switches, mobile networks were built using the Release 99, R99, standard, where the Mobile Switching Center, MSC, was a monolithic hardware block, similar to a 5S. The soft switch changed this in the 3GPP Release 4, R4, era and beyond. 1. The birth of the distributed MSC. In traditional 2G/3G networks, the MSC handled everything: the signal to find your phone, the actual voice path, and the billing. The soft switch broke the MSC into two parts. MSC server, MSS, the control logic, soft switch. It sits in a central data center and handles signaling, mobility management, handovers, and subscriber authentication. Media gateway, MGW, the switching fabric. These are distributed geographically, closer to the cell towers. They handle the actual voice traffic, the bearer, and convert it to IP packets. 2. Unlocking local switching. This architectural split significantly reduced costs for mobile carriers. Legacy problem: in a monolithic architecture, if two people in the same small town called each other, their voice signals had to travel all the way to a central big city MSC and back. Soft switch solution: The MSC server in the big city controls the call, but it tells the local media gateway in that small town to connect the two callers directly. This saves the carrier massive amounts of backhaul transmission costs. 3. Paving the way for VoLTE and IMS. The Softswitch was the stepping stone to VoLTE, Voice over LTE. By moving the mobile core to a Softswitch architecture, voice was already being treated as data inside the core network. This allowed for the introduction of IMS, IP Multimedia Subsystem, which is essentially a giant, standardized Softswitch cluster that handles all communications, voice, video, and text over 4G and 5G. For scalability and pooling, Softswitches introduced the concept of MSC pooling. In the old hardware days, if one MSC failed, every cell tower connected to it went dark. With Softswitches, multiple MSC servers can form a pool. If one server goes down, the others automatically take over the signaling for those towers. This created the always-on reliability we expect from modern mobile networks. Summary: the evolution of mobile core feature pre-Softswitch, 2G/3G R99, post-Softswitch, 3G R4/4G, MSC structure monolithic, control plus bearer, distributed, MSS plus MGW, voice transport TDM/dedicated circuits IP/packet-based backhaul use high, hairpinning to central office, low, local switching at the edge, reliability N+1 redundancy, expensive, pooling/virtualization, efficient. In summary, why Softswitches emerged? Softswitches emerged because telecom networks needed IP-based voice transport, separation of call control from media switching, lower cost and easier scaling compared to TDM, hardware support for new services, VoIP, video, unified communication, integration with broadband and mobile IP networks. Essentially, Softswitches replaced traditional hardware switches, 4S/5S, by moving telephony intelligence into software running on IP networks. Softswitch and Media Gateway. Here is a clear ASCII diagram showing Softswitch, Media Gateway, SIP endpoints, and MGCP. The diagram shows how SIP endpoints communicate directly with the Softswitch, while TDM/PSTN endpoints communicate through a Media Gateway controlled by MGCP. Softswitch architecture diagram: plus Softswitch, call control/SIP server plus application server, plus SIP signaling MGCP, gateway control, VV plus SIP endpoints, Media Gateway, IP phones, PBX, RTP media, TDM left right arrow IP conversion, soft phones, SBCs, plus TDM circuits V plus plus PSTN/TDM lines, analog, DS1, E1, plus plus. How to read this diagram: 1. Softswitch performs call control, routing, registration, and service logic. Speaks SIP to IP endpoints. Sends MGCP/Megaco H.248 commands to control media gateways. 2 SIP endpoints examples: IP phones, soft phones, SIP trunks. PBXs use SIP to register and set up calls via the Softswitch. Send media directly to each other, RTP, unless a media server or SBC is used. 3. Media Gateway, MGW, converts TDM left right arrow IP audio. Does not make routing decisions. It's controlled by the Softswitch. Controlled by MGCP, or H.248/Megaco. 4. PSTN/TDM lines, legacy circuit switched network. MGW bridges these old circuits with new VoIP networks.